So good morning. This morning I will talk about measures of IRT model fit. And we have to start somewhere. So we have to start with IRT. So what are IRT models? Most of you, I understand, have already been acquainted with that. So they are stochastic models for responses of persons to items. They relate item observations to unobserved parameters, unobserved variables. And an important feature of IRT models is the aspect of parameter separation, that you kind of distinguish between the influence of persons or students on the responses and the influence of items and the difficulty of items and even maybe the structure of items. So parameter separation is one of the essential things that defines IRT. To give you a little flavor of it, some of you have seen this and others may have not. So to get an idea of a stochastic model and what that is, I have here a little questionnaire. It's a questionnaire about measuring body height. We can do that with a ruler, of course, but it's, of course, much more fun to do it with a questionnaire. And here you see a questionnaire with questions that all relate to body height. So the first question is, I bump my head quite often. So you can say yes or no, and that answer probably depends on the length of your body length. The second question is, for school pictures, I was always asked to stand in the first row. If you are very short, you are asked to stand in the first row. But there's a stochastic element in it. It's not deterministic. It's not always that if you are very short, that you are asked to stand in the first row, because maybe you are a very ugly child and they want to hide you and put you in the back. So there's always a stochastic element in it. And so it goes on. So it says, in bed I often suffer from cold feet. That is true. If you are too long and the sheets are too short, you suffer from cold feet. But it also depends on your wife. If she always takes all the blankets, you suffer from cold feet, even if you are very short. So there's a stochastic element. So all these questions measure somehow body length, and then IRT is a situation where you can map the responses onto a latent variable, which is length. And the simplest model that we have for that is the Rush model. So this is the Rush model for measuring body length. And it says that the probability of a yes response depends on two parameters, on a theta, which is your length, and on a beta, which is the difficulty of the item. So you could say it's the extent to which you dominate the item, to which you can say yes to the item, depending on your length. So we have responses, we have the length, and we have, you could say, the height of the question. I bump my head quite often. That question has a certain height. Are you over it or not? So the longer the person, the higher the probability of a yes response. So in the end, you map all the people and all the items on a common scale. And here you see this common scale. There's items on it, 3, 7, 5, 9. That's a list of items. And there are people mapped on that. And then you could say, for instance, that Jim is the shortest. Jim dominates item 3, 7, 5, 9, and 11. So there's a positive probability, well, it's always positive, but there's a probability larger than 50% that Jim says yes to these items, but he is too short for item 13 or 1 or 18. There the probability is lower than 50%. And N is a little bit longer, so N dominates a couple of more items, and Joe is the longest because he has, for instance, a 50% probability of saying yes to item 6, but not to item 21, 6, or 16. So this is the Rush model. The Rush model defines a set of response curves. On the x-axis you see the latent ability scale, so that would be length, it's a latent variable. And on the y-axis you see the probability of a correct response, the probability of a yes response. And what you see, the two curves are two response curves for two items. And one of the things of the Rush model is that these curves never cross. So they're always kind of logistic curves which are shifted. They never cross. And that means that everywhere on the latent scale, the order of the probabilities of correct responses remains the same. And that is a property of that model, and that property can be violated. And there we come to the point of model fit. So how could it be violated? One of the things that could happen, for instance, is that the response curves would cross. So for a very low ability, this item is the most difficult item, and this item is the easier item. And for a high ability, the order is the other way around. So that is a violation of the Rush model. The Rush model does not imply that. So you would need a more complicated model to model that. Then there's another way of violating it, and that has to do with, very often with multiple choice items. And there, even if you are very low on proficiency, you still have a probability larger than one of giving a correct response to an item, because you still have the guessing probability for giving a correct response. Yeah, so no matter how stupid you are, you still have a probability of giving a correct response. So that would be, for instance, the 3PL model, the 3-parametric logistic model, and it's identified by 3 parameters. There's a guessing parameter that defines this lower asymptote, so this guessing probability. There's an item difficulty, which defines the position of that curve on the latent scale. And there's a discrimination parameter that defines the steepness of that curve. So that was a very short introduction to IRT models before we come to model fit. Then the final sheet in this introduction is what are these models good for? And well, I've mapped here a couple of points. The first one is test construction. IRT gives you the possibility of choosing items to match a certain test objective. So your objective could be something like pass-fail scores, so cutoff scores, or it could be selecting people with very low proficiency, or it could be estimating the mean of some population regarding their ability. These are test objectives, and IRT gives you a possibility to construct an optimal test. Second one is modeling measurement error. That has to do with the fact that if we take measures like IQ or math ability or even your attitude towards capital punishment, these are all latent variables. They have measurement error, and that measurement error has to be modeled if you subsequently want to use it in analysis of variance or covariance or regression analysis, whatever that you want to do, structural equation modeling. In all these cases, you have to account for that measurement error, and IRT is a very useful tool for that. That is also the reason why IRT now also appears in software packages for instance, structural equation modeling like M+. Yeah, you can do IRT there. Why is that? Because in these models that are estimated there, the measurement error has to be taken into account, so they plug in an IRT model. The third one is incomplete designs. So not everybody has to respond to the same set of items, and still you can map everybody on a common scale. And an extreme example of that is computerized adaptive testing, where everybody gets their own optimal individual test from an item bank. Fourth is test equating, so comparing the scores on different test versions and still be on a common scale. And a fifth application is test fairness. So that has to do with detection of differential item functioning. So detection of items that disadvantage certain groups of students. So these are a couple of things that they're good for. IRT models are built on assumptions, and ideally it would be nice if we could test these assumptions one at a time. In practice that's not possible because somehow the assumptions are a little bit confounded, but taking into account which assumptions you're targeting can help you interpreting the outcome of the tests. So, what are the testable assumptions? First one, there's the form of the response curve, because we saw these trace lines, these response curves, so they had nice logistic shapes, but one of the questions you might ask, is it appropriate? Is the probability of a correct response really properly modeled by a curve of the form that we are considering? The second one is population invariance of item parameters. We assume that for some population the item parameters are the same, so that the responses of people from this population are modeled and mapped to the same common scale. So the item parameters have to be invariant, and we have to test that. The third one is a rather technical one. It's local stochastic independence. And that has to do with the fact that, first of all, it is assumed that given theta, the responses are independent. Well, that sounds very technical. What could that mean? First of all, it means that there's no dependence between item responses in the sense that a correct response on one item implies a correct response on the other one, so that you're helped by a correct response on the preceding item. Then fourth, sometimes IRT models are enhanced with an assumption about the ability distribution. So sometimes you say, well, this group of students has a normal distribution of ability, and another group of students has another normal distribution of ability. And also that assumption has to be tested if you do the analysis. Is it appropriate or not? And then the fifth one is dimensionality. Usually we use unidimensional IRT models, but in many situations there's also a need for multidimensional IRT, so for multidimensional latent abilities. And that can be within a test, but IRT can also be used to estimate the correlation between two latent variables. Suppose I have a test for IQ, and I have a test for math ability, and I want to compute their correlation on the latent ability scale, then I can also do that using a two-dimensional IRT model with a dimension for IQ and a dimension for math ability. That's also an important application of IRT. If you run an IRT package, a dedicated IRT package, then like for instance IRT Pro is an often used package at the moment. Then you get a table, and in that table are there's information about model fit, and usually that information is communicated in terms of observed and expected responses. So for instance here I have an example of a package that we will be playing with somewhere in the coming days. That is the MIRT package, and you see that there is in this test 10 items. So here are the item numbers in the first column, and then here you see, for instance, that the package has distinguished two groups of students, group 1 and group 2. So you could say the boys and the girls, for instance. And what you see then is under expected, let's start with observed. For item 10, for the, say, group 1, which is the girls, there are 16 correct responses. And the IRT model predicts there's 15.4. So the IRT model is very close. And then what you see here is a residual, so that's some kind of weighted difference between the two. If these two are close, the model fits, and if it's very far apart, then it doesn't fit. And you could also do that for the second group, and you also get residuals, and sometimes that is also accompanied by a item fit statistic, that is the two last columns, so you see an outcome of a statistic and some kind of significance probability that tells you a little bit about model fit. And then here at the bottom you also see some kind of overall statistic. So that's the kind of information that you very often get, and what we will look at now is a little bit more in detail what kind of information that could be and what the various ways are to obtaining that. Statistically, it's nothing, testing IRT is statistically nothing like testing any model in statistics, and in statistics we usually test models by assuming a general model and a special model. And the special model is usually here in this situation an IRT model. So that IRT model has parameters, let's call them phi1. And the general model has more parameters. A more general model is always built on top of a special model, so it's an IRT model, but it has more parameters in it, and we are going to compare these two models. And so in the case of the special model, the extra parameters in the more general model are zeros. So special model is an IRT model, the alternative model or more general model is also an IRT model, but there a model assumption is violated. So one of the assumptions that we are targeting, say the form of these response curves, is violated, and that is reflected in extra parameters. And then we test the null hypothesis, whether these extra parameters are zero or not. So that is the whole principle behind testing IRT models. Then in statistics we have three big families of test statistics that we can use, and we will go over them for IRT one at a time. First one are likelihood ratio tests. In likelihood ratio tests you estimate both models and you compare their fit, so you estimate in general model and you estimate the IRT model, and you make some inferences about the ratio of these two, the likelihoods of these two models. The second one is a Wald test, so that needs an estimation of a general model. And the third one is a Lagrange multiplier test that only needs estimates of the special model. These three families, the outcomes are what's called with a technical term asymptotically equivalent, so they are giving you comparable chi-square values, values for the test statistics, only their application is a little bit different. In one situation you choose for one statistic, and another situation you choose for another statistic, and so they all have their own application. This is a test from the first family that I will be discussing, and this is a Lagrange multiplier test. And Lagrange multiplier test, what exactly that is, I will come to in a moment, what it technically is. But I first describe it a little bit, and then I'll also show you some outputs where you can see that. So it's a test for differential item functioning. That's another word for parameter invariance. So it's a test for comparing the estimates in one group with the estimates in another group, and deciding whether one of the groups is disadvantaged or not. I need an alternative model, and here I've defined it for the 2PL model. The alternative model is a 2PL model with an additional difficulty parameter for what is called the focal group. The focal group is usually the disadvantaged group. And so we define a background variable, and it is x, and it can be 0 or 1, and it is 1 if you are in the focal group, and it is 0 if you are in the majority group. In the reference group, it's very often called. And what you see here is the 2PL. So it says the probability of a correct response by a student I to an item k, the probability that it equals 1, and it depends on parameters, but now also on this background variable. And what you see here is the 2PL, so you have A multiplied, so the discrimination parameter A multiplied by theta minus B, which is the item difficulty. But now we added a covariate, that was gender, that was the background variable, and it assumes a value 1 if you are a girl, and it's multiplied by a parameter delta, and that parameter delta kind of gauges the effect of being a girl. Yeah, so it's a kind of a shift of the item response curve if you are female. Then there is a null hypothesis, and the null hypothesis is that this additional parameter is equal to 0. So the null hypothesis is there is no diff, that the same 2PL model holds for both the boys and the girls. And then it turns out that if you use a Lagrange multiplier test, and I will define that statistic in a moment, but it's a rather technical definition, so it's not important here in this framework, but just to be complete, I will define it in a moment. But if you do all the arithmetic, then it turns out that the test for that null hypothesis can be based on a difference between observed scores and expected scores. The observed scores here is the sum over all individuals, so over all students. It is the covariate X multiplied by the item response. So this is, and this is only 1 if you are a girl, so this is something like the number of correct scores given by the girls. Number of correct scores given by the girls. And it's compared with the expectation under the IRT model. So you see here again a summation over individuals, and then you see here, so you multiply it again by this background variable, and what you see then here is the expected probability of a correct response given theta, given the responses that you have observed. So that is an expectation under the model of the number of correct responses by the girls. And of course you can divide this by the number of girls and also this by the number of girls, and then you could get here a proportion and here a kind of an estimate of a probability. So to make that a little bit concrete, also then gives you an idea of how this could work in practice. This is an output of software, and what is important here is there are 20 items in this design. So this is a test situation where we have 20 items. Then I have 4 booklets in the design. What booklets are, I'll explain in a moment. And there are 2 distributions of ability. That is important. Suppose that this is boys and girls also in this output. Differential item functioning does not mean that the ability distribution for the girls and boys should be the same. They can still be very different in proficiency. But given a certain ability level, there must be no difference in the probability of a correct response, because that would be differential item functioning. So they can still be very different in proficiency. Then we scroll down a little bit and we get some echo of the data that we are looking at. For instance, for item 1, it says here, this part, that there are 2,000 respondents responding to that item, and that 1,298 give an incorrect response, and then 702 give a correct response. And then you get the last column, that is the design. I told you there are 4 booklets. Well, a booklet is a set of items. So there are 4 different set of items used here in this analysis. And the 2 ones mean that the item was present in the first 2 booklets, booklet 1 and booklet 2, but it was not present in booklet 3 and 4. And so the information goes down. For instance, item 8 was present in all the booklets and responded to by 4,000 students. And item 20, for instance, was present in the last 2 booklets. Yeah, so that was the design. Then we scroll down a little bit lower. Here we get parameter estimates. Software here that I use always estimates the Rush model first, then the 2PL, and then a multidimensional model. And then, so this is the Rush model, we get parameter estimates, and then we get some estimates of the proficiency level of boys and girls. So mean, it says that the mean proficiency level for group 1, the girls, is 0.8 on the latent scale. And then if we go a little bit further down, it says for the second group, the mean was 0. So in this case, the girls are more proficient, so they're higher on the latent ability scale. And then we scroll down a little bit further, and then we get this information of this Lagrange multiplier test. So this is, for instance, for item 1, it says, this first row here, it says that the proportion correct for the girls was 0.30, so this is this number, that the expectation under the model was 0.32. For the other group, it was 0.40 as an observation and 0.38 as an expectation, and then there's some kind of difference, and there's a test statistic that tells you a little bit about model fit. What I should say here is that you get test statistics, you get really chi-squares with a significance probability and stuff like that, but that is not the most important part of this computation. And that has to do with the fact that if you have a very large sample size, like in the PISA project there are 500,000 students, then everything becomes significant. So in practice, this last number here, which is the effect size, that's some kind of indication of the size of that difference between observed and expected, is much more important. And as a rule of thumb, you could say that difference should be smaller than 0.10, for instance, that it would be a reasonable cutoff score for deciding on whether the item has differential item functioning or not. So he does do that for the first booklet, and then for the second booklet, third booklet, fourth booklet, and finally there's also some overall statistic. And what you see here is all the effect sizes. This is this column here, this thing. All the effect sizes are small, so in this case there's not much diff under the Rush model. That's the conclusion. And then the software goes on with computing stuff, and then comes to the 2PL model, and then you get exactly the same kind of table, but then for the 2PL model. So here's the table for the 2PL model. It's the same kind of table, same layout. And here you can also see a little bit whether the 2PL model did improve the situation or not. Well, we were already in a very good situation, so there's not much room for improvement, but you could kind of compare the overall fit, with respect to diff, for the Rush model versus a more complete model. And then the software goes on here. In this case, we also had a multidimensional model, so here he estimates the multidimensional model, and then once again, here you get the same table, that one, but then for a multidimensional model. So that means you added latent variables, and then you can see whether did it improve or did it not improve. Then you could ask, testing this hypothesis with this Lagrange multiplier test, whether this delta is 0, of course, you could do that also with the other test statistics. You can do it with a Wald statistic, you can do it with a likelihood ratio statistic. But in this specific situation, we use a Lagrange multiplier test because you saw that for all the items, all the tests were computed one at a time. And if you would do that with a likelihood ratio test, you would have to do the test you have to have a new estimation of that delta for every new hypothesis, and you don't want that. So Wald tests are very practical for other things. We will come to that in a moment, and also likelihood ratio tests have their application, but this typical table would be something that would be computed with a Lagrange multiplier test. Now, this is a model for local independence. So once again, it is a model, this is once again the 2PL model. It has the probability of a correct response. And in this specific generalization of the model, we assume that a response on an item depends on the response on a previous item. And you can see that happening here. So we are looking at item k. So here we have the A times theta minus beta for item k. So this is a 2PL model, this is for item k. And then we add a parameter. That parameter is delta. And that delta is a regression coefficient for the regression on the previous item. So here you see item response I k minus 1. So this is the response on the previous item, and that response predicts the response on the current item. And that is a violation of local independence. So if that delta is not 0, then the model is violated. You have a violation of local independence. Yeah. And if you would do all the computations and look at what your statistic is, then you would see that the statistic depends on the product of the response on item k minus 1 and the response on item k. So this is the number of times that item k and item k minus 1 were responded to correctly. Yeah, so it's a kind of a simultaneous realization of these two items. And on the right-hand side, you have the expected value under the model. Now, if you look in the software, then what kind of output would that create? Go up a bit and search for it. Yeah, here it is. So here, for instance, in this table, he tests on previous items. So item 2 is in this blue part, the item targeted, and item 1 is the item predicting the response on item 2. So it's item 1 and item 2 together. And then the columns work like that. You see item B is 0, item B is 1. So that has to do with the response on item 1. Item 1, the response could be a 0 or the response could be a 1. And then you have the average score on item 2 for people who score 0 on the previous item, and the average score on item 2 for people who scored a 1 on the previous item. And these two numbers are then compared with the expected value under the model, and that gives an indication of the extent to which the local independence assumption is violated. So that is another test, and in some situations that could be an interesting one if you really think that the items depend on each other. And so it goes on. This is a formula for the response curves. I'm not going to dig into that formula, but just look at the output, because the formula is a little bit difficult to explain now. So this, for instance, is kind of the output. How does this work? This is item 6. And what the software does do is he wants to evaluate whether the response curve is correct. So whether the probabilities of correct responses vary across the latent scale as predicted. Then what he does do, as a proxy for theta, creates 3 score groups. So the low scoring students, the average scoring students, and the high scoring students. So that is what you see here. It says group 1, group 2, group 3. And then he looks at this row for these 3 groups, and the expected average score for these 3 groups. And then you see, for instance, in the low scoring group, you observe 0.71 and you expect 0.65. And then in the average scoring group, group 2, it's of course a little bit higher because they have a higher proficiency. And there we have 0.87 versus 0.82. And then finally in the high scoring group, we have 0.95 and 0.91. And then finally, here at the end of the table, in this column here with labeled absolute difference, there's some kind of effect size that tells you how bad it is. And then finally, you also get some chi-square statistics that tell you a little bit more about that. And so it goes on. If we look further in the output, then, for instance, if we scroll up, we see here another table that has the same form of expected and observed. Here, for instance, this is a test for whether the ability distribution was properly modeled. So what you see here is score ranges, 0, 2, 3, 4, 5, up till 14, up till 15. And then you see a frequency distribution, so that is the number of students attaining such a score. And you see the expectation under the model. And the frequency distribution and its expectations should, of course, match. They should be close enough. So that is also a Lagrange multiplier test. And here at the bottom you get an outcome of the test, and you get a significance probability and stuff like that. Okay, so that is the whole story about Lagrange multiplier tests. And then we go to the next one, but before we do that, there's a final sheet which I will go over very quickly because this is a rather technical one. So, but just for those of you who want to hear that, so there's a null hypothesis that a set of parameters phi2 equals a constant, and the constant is 0 in this case. The test is based on the first order derivatives of the log likelihood function regarding all parameters, including the parameters violating the model. And then there is a variance-covariance matrix for that first order derivative. And there's a statistic that is a quadratic form in these first order derivatives and the covariance matrix of these estimates. So that is how the stuff is computed. But that's technical stuff, and we skip that. Then wall tests. Wall tests come with pictures like these. Suppose that we have, again, boys and girls. So again, we have 2 groups, and we estimated the model in the 2 groups, and we draw a picture of the parameter estimates. And what you see here is an example of real data. This is from a multidimensional model. And so it's a 3-dimensional model. And here you see the correlation of A parameters on the 3 dimensions. This is the correlation between item location parameters on the 3 dimensions. And what you would want is, so this is the x-axis is the estimate for the one group, and the y-axis is for another group. And what you would like is that there would be a straight line through these two, through this scatter plot of these two, because you would like the parameter estimates to be the same in the two groups. And so this is real data, a real example. This is a test for fatigue for patients with rheumatoid arthritis. And you see here that also the correlations between the two sets of parameter estimates, and between the brackets is another correlation, and that is when 2 or 3 extreme items were removed from the set, and then you see that the correlation goes up. So the correlation is not very high, and if you remove some some items that do not fit very well, then you see it gets better, the correlation gets higher, although that doesn't happen everywhere, because in that test there was one dimension that did not work very well, and that you can also already see that in the scatter plot. Scatter plot doesn't really look like there is a lot of dependence between the two estimates. And then if you remove some items, it gets worse. Yeah, so that dimension is problematic. There's a problematic dimension in it. So this is for the item locations. That worked quite well. Then you have the scatter plot for the A parameters. This looks much worse. Yeah, for dimension 1, it would still be acceptable, but for dimension 2 and dimension 3, it is much worse. And that has to do with the fact that A parameters are much more difficult to estimate than B parameters, than item location parameters. So this did not make us very happy that correlation was quite low. Then we wondered, by the way, so the model does not fit very well. Then we would wonder how much effect would it have on theta estimates. And then we came up with this plot. This is, yeah, I must explain this a little bit more about what the design was in order for you to understand it. This is theta estimates with 2 sets of item parameters. One of sets of item parameters was obtained in a linear test, so with paper and pencil, and the other set of item parameters was obtained in a computerized adaptive test. And the diff would be something like the difference between the cat situation and the original linear situation. So the parameters turned out, the item parameters turned out to be quite different, especially the A parameters. But then we wondered how much difference would that make for the theta parameters. Then you can make a plot like this one, and then you see here the situation for the first dimension. So there's, for many students, it does not make much difference, but still here on the outskirts there's a lot of noise. The second dimension, it's a bit worse, and as we expected, the third dimension is quite problematic. Yeah, so that is the kind of stuff about model fit that you could look at also. And the basis for this is a wall test, because you have 2 sets of parameters. So what is the general definition of a wall test? A wall test looks at functions of parameters and tests the null hypothesis whether these functions are 0. So this is very general. Make it more specific, suppose that is the parameter estimates in 2 groups, so then that function is the difference between a phi1 in one group and a phi2 in the second group. So we test whether these 2 parameter estimates are the same. Then the wall test is again a quadratic form, and so it's here, that's the bottom line, a quadratic form in the difference between these 2 parameter estimates, and then weighted with the variance-covariance matrix, and that leads to the wall test. And by the way, it also leads to something which we have not drawn, but in principle these are estimates, and in that wall test we also have the standard errors of these estimates, so we could draw little standard errors around every estimate okay, to see whether how far it is from the line that we could draw through that scatter plot. But in this case, of course, that's not very useful because you don't need you don't need standard errors to see whether this and this is very wrong. Yeah, and also it would just clutter up the plot. We now have had two families, so we had a Lagrange multiplier test, a wall test, and then finally the question would be what kind of use could we have from a likelihood ratio test? So what is a likelihood ratio test? For instance, we could test hypotheses about population models. So a likelihood ratio test, it is defined as -2 the log of the likelihood under the restricted model and the likelihood under a more general model. And we will look at the output to see how that could work. For instance, here we want to test about the Rush model versus the 2PL versus a multidimensional model. And the first thing that we see here, this thing is called the iteration history of the estimates, the estimation procedure. And here in this small example, this is not a problem. But if you have real data and start analyzing, then this is a very important set of numbers. Because what you see here on the right-hand side is the log likelihood. And you see that the program starts somewhere with a log likelihood and then slowly moves into the direction of what is called the maximum of the likelihood. So he searches for the maximum. And this is the number that he finds. And on the right-hand side here, on the left-hand side, sorry, we have the change in that likelihood. And the conclusion is here, after 20 iterations, after 20 steps, he has converged, he has found the maximum. Yeah, and then you're happy. But if you have more data, and if the model is not so smooth, let me put it that way, then that could take much longer. Yeah, then he might not get there in 20 steps or even 40 steps or even 60 steps because this number here remains big. Yeah, and then you have to make many more iterations. Yeah, you have to search for the maximum of that likelihood. But you cannot do any inferences if the model has not converged. So if there's not a very small number here for the convergence, then you should either stop or search longer because you only can make inferences as long as you have really attained the maximum of the likelihood. But anyway, for the Rush model, this is the number here, this is the maximum of the likelihood. And I put this here in a table, so this is here for the 1PL, 20 items. We have here for the Rush model the log likelihood, and here in the next column we have -2 times the log likelihood, because we will need that to compute a test. Then, to compute this test, we have to know how many free parameters there are in the Rush model. Yeah, and we have here 20 items. So, for 20 items, we have 20 item parameters. We have 20 B parameters. Then, we had 2 ability distributions, say one for the boys and one for the girls. How could we envision such a model? So, suppose that this is our theta scale. And here we have, again, for 2 items, so this is 1, the probability of a correct response for 2 items. And what I usually do is draw the ability distributions upside down. So this is for the boys, this is for the girls. Yeah? Now this latent variable does not exist. Okay? We cannot observe it. It's not like length. It's like latent length. You cannot observe it. So we have to identify that scale. We have to say where the origin is. And in fact, we also have to, from that scale, we have to define what is called the scale, that's the stretch, something like that. And in the rush model, the program defines the scale by saying that the average of the second distribution is 0. Yeah? And then we have here the standard deviation for that second group. Here we have the mean for that second group and the standard deviation. So here we have a mu. So then the model is identified. We know where the origin is. It's an arbitrary origin. And we estimate this mean and these two standard deviations. So that is 3 population parameters. So we have 20 for the items and 3 for the population distributions. And that's what it says here. It says 1 for the mean and it says 2 for the ability distributions, for the variance. And that leads to a total of 23 free parameters in a rush model. Then we go on, and in the output, so then he gives all the fit statistics, and then at a certain point he starts estimating the 2PL, which is a much more tedious process, by the way, than the rush model. If you do it optimal, you can estimate the rush model in a nanosecond, and this one takes longer, much longer. But also here he converged, and then you see, first of all here, the -2 log likelihood, and here you see estimates of, for instance, the A parameter and the B parameter. So this log likelihood here I put in the table, and I come up with this number. And then I start counting the number of parameters in my model. Now, for the items, the number of parameters is twice as much because we have A parameters and B parameters. So we have item location and item discrimination. So that's 40 parameters. Then we have one mean, of course, because we have to identify where the origin is. But now we only have one variance, because if you look in the output, you can see also that here for the second population, the standard deviation of the ability is fixed to 1. And the question is, why is that? Well, the reason behind that is as follows. Every item response curve also has an A parameter, and that A parameter defines the steepness of that curve. Now, these A parameters are estimated, and suppose that we also would estimate these two standard deviations. Then the model would not be identified. Why is that? Because then I can stretch the scale. If I stretch the scale, these A parameters go down, yeah, it becomes more flat, but these can go up, the standard deviation goes up, yeah, and the fit is just as good. Yeah, so there is stretch in the scale, and we have to fix that stretch. And we can fix it in several ways. We could say one of the A parameters is 1, for instance. But that's not a good idea for various reasons, and therefore we say that one of the variances, and in this case for the last ability distribution, is equal to 1. So that's what we have. Then we have 42 parameters for the 2PL. We have a log likelihood, we have a -2 log likelihood, and then we could compare, compute a log likelihood function of the 1PL versus the 2PL. There would be a difference between these two numbers, and the difference between the number of free parameters, that would be 19, and so this has a chi-square distribution with 19 degrees of freedom, and that difference is so big that the rush model is rejected. This is purely statistical reasoning. It has the same power problem as we were just discussing. So you could do it in this way, but of course you always have to keep in mind, are these differences important or not in terms of effect sizes? Is it really very important? Are the parameters really so much different? Then finally, if we scroll down further, we get the output of a multidimensional model. And so that even takes even more and more time than the 2PL, so that takes quite a long time. But in the end, we get an estimate here, this part. So we get a log likelihood. And for instance, what we have here, this part here, marginal 1. So this is for the first group, the mean on the two latent dimensions for the first group, so for, say, for the girls. So the girls are 0.6 and 0.8 on the two dimensions. And then here you have the covariance, the estimated covariance matrix for that girls. And here it's translated into a correlation matrix. So the correlation between the two latent dimensions for the girls is 0.88. 0.88. Yeah, and here the same story for the boys. So for the boys, the mean is fixed to 0. And secondly, the covariance matrix is constrained to a correlation matrix in order to identify the scale. And then you see that the correlation for the boys is higher between the two latent dimensions. And also the boys have a lower value of ability on the two latent variables. So that gives us a second test. We could test, for instance, the 2PL against the multidimensional model. And here we count the number of free parameters. And we get a likelihood ratio statistic. And we get a degrees of freedom. And also in this case, the complicated model, the multidimensional model, is well, let me put it another way. The 2PL is rejected against that more complex model, so that more complex model has more statistical evidence for it. So this was a kind of a summary of ways in which you can test the fit of IRT models. It is directly derived from statistical theory. It goes with nothing special. There's nothing special involved there. But an important point to keep in mind is that this coin has two sides. First of all, you really have to give evidence that your IRT model fits. So you have to make clear that the inferences that you make are valid. So if an IRT model does not fit, it is really not valid. You have to give some evidence that it fits. But on the other hand, fit is relative. I mean, very strict statistical testing has a power problem, and you also have to have enough fit. So the perfect fit would be a model with an enormous number of parameters in it, and at some point you decide, well, the data are represented well enough. You can see that in the tables that we are looking at, and then you decide, well, this model is acceptable for the inferences that I want to make. So that says that a fit to IRT model is both science and art, and that is where I want to stop. Thank you.